All right, let's break down how to find the union of two sorted arrays. Now, there's the common way to do this, and then there's the optimal way. The one that's going to impress in an interview. We're doing it the optimal way. And let's get right to it. Most students really do overcomplicate this with sets. Look, I get it. Your first instinct is probably to just throw everything into a hash set to deal with the duplicates. And sure, that works, but it's kind of an efficiency trap. And interviewers, they know to look for something smarter. So we're going to bypass that method completely. So just so we're all on the same page, what are we trying to do here? The goal is simple. End up with one single list. It needs to have all the unique numbers from both of our arrays, and it has to be sorted from smallest to largest. That's it. Okay, so these are the arrays we're going to be working with. We've got R1 and R2. Notice they're both already sorted, which is a huge clue. But also, look closely at R1. See that duplicate 2? That is the key. How you handle that little guy is what really separates a decent solution from a killer one. So, what's the secret sauce here? It's all about something called the two-pointer approach. I like to think of it as a little dance. We're going to have one pointer, let's call it I, for the first array, and another one, J, for the second. The way they move together, it's super elegant and crazy efficient.
All right, let's get this set up. Step 1 is just initialization. We put our I pointer right at the start of array 1 and the J pointer right at the start of array 2. Our final union list? Totally empty for now. Ready? Let's dive in.
First move, we look at what I and J are pointing to. That's a 1 and a 2. So which one's smaller? The 1, obviously. So we take that 1 and add it to our union list. And here's rule number 1. Whenever you take an element, you move its pointer forward. So I gets to take one step to the right. Okay, next comparison. Now I is pointing at a 2, and hey, J is also pointing at a 2. They're a match. When they're equal, the rule changes a bit. We add the value, just once of course, to our union. And then, here's the important part, both pointers get to move forward one step. They move together. And here we go. This is the moment. Pointer I just moved to the next spot in R1, and what's there? Another 2. But wait a second. Our union list already has a 2 in it. So what do we do? If we just follow the rules blindly, we're about to mess up and add a duplicate. This is where the magic happens. Here's the trick. Before we even think about adding a number to our union, we ask one super simple question. Is this new number different from the very last number I put in my list? That's it. That one little check is our secret weapon against duplicates. Okay, let's see this trick in action. Right now, I is at that second 2, and J is at 3. The normal rule says the smaller element, the 2, should be considered. But we do our check. What's the last thing in our union? It's a 2. Since they're the same, we skip adding it. We just move pointer I forward and pretend it never happened. See? No duplicate. So clean.
All right, next up. Now I is pointing at a 3, and so is J. They're equal again. So first, we do our check. Is 3 different from the last number we added, which was 2? Yep, it is. So we add the 3. And since they were equal, what do? That's right, both pointers move forward.
The dance keeps going. Now I's at 4, J's at 5. 4 is smaller. Is it different from our last number, 3? Yes. So in it goes. We add the 4. And because the value from R1 was smaller, only pointer I gets to move. And that's it for array 1. Pointer I has now walked right off the end of its array. It's exhausted. So the main comparison part of our dance is over. What's left? We just have to clean up. We look at array 2. Is there anything left? Yep, pointer J is still sitting on that 5. So we just scoop it up, add it to the end, and we're done. And there it is. Take a look. Our final union list has every unique number from both arrays. There are no duplicates, and it's perfectly sorted. And the best part? We did it all in one single, super efficient pass through the data. So that's the logic. But what does it look like as code? Well, here it is. It's actually pretty simple when you break it down. You can see that main while loop, that's our two-pointer dance. Inside, you've got the if-else conditions for comparing the elements, and then at the very end, those little loops are just for grabbing any leftovers. This code is a direct translation of everything we just walked through. So why did we go through all this trouble instead of just using a set? For this. O of n plus m. This is the big prize. This is the time complexity we were aiming for. All it means is that the time it takes is directly proportional to the size of the two arrays combined. We basically just walk through each array once. That's it. So why is this so much better? A couple of reasons. First, we just make one single pass. We don't have to go back and forth. Second, and this is huge, we don't create a whole new data structure like a hash set. That means less memory overhead, which can be a massive deal with really big arrays. We're just iterating and building our list as we go. It's linear time, and honestly, you can't really get faster than that for this problem.
Look, this isn't just some random algorithm. The two-pointer technique is a fundamental pattern you'll see over and over again. And nailing this problem, especially that little trick for handling duplicates without a set, is exactly the kind of thing that makes you stand out in a coding interview. So for real, save this merge trick for interviews. It's an absolute game changer.